Hello everyone, this is Lecture 8 of ComSci 123, Binary Trees. In today's video, we will first introduce the tree ADT, and then later on, we'll focus our discussion on a specific type of trees, which are the binary trees. We will also look at how to implement binary trees using arrays and a linked structure. Finally, we will also look at some tree traversal algorithms. Okay, so let's start. So this is already our 9th ADT in ComSci 123, which are the trees. But these are not the trees that we are talking about, okay? So the trees that we are talking about are these types of trees, okay? So you've probably seen this data structure already in your life as a ComSci student, okay? So these trees are what we'll be discussing. So trees are nonlinear ADTs, and it's made up of nodes with parent-child relationships. Okay, so each node has one parent, while a node can have several children. Okay, and trees are used to model a hierarchical structure. Okay, because there's a parent-child relationship. Okay, so yeah. Now, first we need to define some terminology for trees so that when we talk about them, we have some common terms, right? Or standard terms. Okay, so let's start with the root. Okay, so the root node is the topmost node and it doesn't have any parents. Okay, so unlike the root of the tree in the real world or in the ones that you see in nature, wherein the root is at the bottom, the root in our tree ADT is at the top. Okay, so you can think of it like as an inverted tree where the root is at the top. Okay, next is something called the internal nodes. So these are nodes with at least one children. Okay, so if you have one or more children, then you are an internal node. Okay, now the opposite of that is the so-called external nodes or leaf nodes. So these are nodes without any children. Okay, so it doesn't matter what level these nodes are, as long as it doesn't have any child, then you consider that a leaf node. Okay, and then next is ancestors. So we refer to this as the group that contains the parent node, the grandparent node, the great grandparent node, and so on. Okay, so you have the parent of the parent, and then the parent of the grandparent, and so on. Okay, so those are the ancestor nodes. And then the opposite of that, of course, is your descendants. So that would include all your children, all of your grandchildren, and so on, great grandchildren, all the way to the bottom. Okay, so if ancestors is going up to the root, descendants is going down to the last level. Okay, next, trees wherein the children of the nodes are unsorted, we call those unordered trees. Okay, so if it's just an unsorted collection of children, like it doesn't matter if A comes before B or comes before C, as long as you know that that's a children of, let's say, node Z. Okay, so those are called unordered trees. But if the children of the nodes have a sorted order, okay, so it's important that A is the left child and B is the right child, or A comes before B and B comes before C, then we call that an ordered tree. Okay, so there is a specified order for the children, whereas in an ordered tree, it's just like a set of children. Doesn't matter which child comes first. Okay, next is the branching factor of a node. That simply refers to the number of children that the node has. So if the node has 2 children, then the branching factor is 2. If it has 3 children, the branching factor is 3, and so on. Okay, so pretty straightforward. Next is the depth of a node, and that refers to the number of ancestors, or basically the distance of that node from the root. Okay, so how deep are you in the tree? So that is the depth of the node. So it refers to the number of ancestors, because if you go from the node to the parent, and then to the grandparent, to the great grandparent, and so on, all the way up to the root, you would that measure or that count would be the depth of the node. Okay. Next is the height of the tree, usually referred to as the variable h. Okay, so this is the maximum depth of any node. Okay, so for all of your nodes, which node has the maximum depth, and then that depth would be used as your height of the tree. Okay, so if the maximum is, like, let's say 5, then the whole tree's height is 5 also. Okay, and then finally, we have something called the subtree. So a subtree refers to a tree that is rooted at some node, and then it refers to the node and its descendants. Okay, so what do you mean by that? So for example, in this tree, we could have a subtree here rooted at C. So the subtree, the C subtree, would be from C, and then its descendants, which are G and H. Okay, we could also have another subtree, like, let's say, the subtree at F. So the subtree at F would include this one right here. So F and its descendants. So that would be I, J, and K. Now, how about if it's the subtree at B? So if it's the subtree at B, it would include B as the root and all of its descendants here. So E, F, and then the grandchildren I, J, and K. So if you call it a subtree rooted at some node, then you start at that node and then include all of its descendants. Okay, so yeah, that's subtree. Now let's also take a look at the other tree terminology terms that we had discussed. So for example, here in this tree, the root here is node A, right? So this is the root. So you notice that this node doesn't have any parents and it's at the topmost. Okay, now how about the internal nodes? So for the internal nodes, I will use probably red. So for the internal nodes, those are the nodes that have children. So that would be B. Oh, probably use another color because it's kind of similar to the orange. Okay, but red is fine. So the internal nodes are here. A, because it has children. B, C, F, and that's it. So those are the internal nodes because those are the ones that have children. Okay, now the leaf nodes or external nodes are those without children, and that would be E, D, G, H, I, J, and K, because they don't have any children. Okay, now for the node depth, the depth of the root would be, for A, depth is 0, right? Because you're already at the root. Okay, so you don't need to traverse because you're already at the root. For nodes B, C, and D, the depth here is 1, right? Because they need to traverse one time to go to the root, which is A. For this level, E, F, G, H, the depth is 2. And then finally for I, J, K, the depth is 3. Okay, so you can divide them into layers. So this is depth 1, this is depth 2, and then this is depth 3. Okay, and then what is the height of the tree? Well, the height of the tree is the maximum depth, which is also 3. So the height of the tree is 3. Okay, so don't be confused by 3 and 3. Okay, and then one last thing, so branching factor. So let me erase everything first. For the branching factor, so what is the branching factor of D? Well, the branching factor is 0 because it doesn't have any children. For C, the branching factor is 2 because it has 2 children. And then for F, the branching factor is 3 because it has 3 children. Okay, Same for A. It's also 3 because it has 3 children, B, C, and D. Okay? So those are the terms for the trees. So some tree terminology. Okay? So I hope that's clear. Now, for trees, there should only be one unique path from the root to any node. Okay? So one path, and it must be unique. And you also need to note that trees are acyclic or acyclic, meaning it doesn't have any cycles, okay, or loops. Okay, so for example, here, the ones here on the top level are legal trees, okay, while here, the ones at the bottom, they are not trees, okay, because, for example, in here, so in the first one, here at the bottom, this node here has 2 parents, right? So let's name them A, B, C, and D. So node D has 2 parents, B and C. So naturally, because you have 2 parents, you also have 2 paths to the root, right? So from D, you can go from D to B, B to A. That's one path. The other path is from D to C, C to A, right? So this is not a valid tree, okay? And then for the second one, this is also not valid because you have a cycle or a loop. So you go from here to here, here to here, here to here, and then here to here. That forms a cycle, right? Because you can take this many times, okay? So if there is a cycle, that is not a valid tree because trees should be acyclic, okay? So yeah, just take note of that. Okay, now some applications for trees include organizational charts because as we mentioned, they model hierarchy. So the organizational chart of, let's say, a corporation, wherein the marketing director is at the top and then some managers are directly under him and then some assistant managers and so on. So that's one example of a tree, right? So the root here is at the top and then has children and then has great-grandchildren and so on. You can also use this in file systems, right? So the root is here and then you have several folders and then subfolders and then subfolders and so on. Okay, so that can also be visualized using a tree. And then in biology, you have organism classification, so you can also use trees to visualize that, right? So you have organisms, prokaryotes, eukaryotes, and so on. And then it also models hierarchy, right? And then next, can also use this for game trees in artificial intelligence. So if you're trying to figure out what the best move is, like for example in tic-tac-toe or in chess, so you make different game scenarios, for example, as your children. So if I make this move, then the game state would be this. If I make this move, then the game state would be this, and so on. Okay, and then you can figure out which move will give you the best possible result, right? So those are just some examples of applications for trees. Okay, now let's talk about the tree ADT itself, the interface. Okay, so for the tree ADT, it uses position ADTs to abstract out the nodes. Okay, so that for the same reason before in list that we used positions, so that we don't expose the underlying implementation, because if you say nodes, then that just means that we're using node-based implementation, right? But what if we use an array? So calling it a node would not be appropriate, right? Because you're not using nodes in arrays. So we'll just call it positions, okay? 3 positions for abstraction. And then each position will hold an item, okay? So only one item per position. And as usual, the position methods are get item and set item. So the getter and setter for the one property, which is the item. Okay. Now for the interface of the tree itself, you have the following methods. So of course you have size, which is the number of items in the tree. Is empty returns true if there are no items in the tree. Okay, so if the tree is empty. And then items would be an iterator to return all items in the tree. Okay, so all of the contents of the tree. Now this is different from positions. It's similar but different because it's also an iterator, but instead of returning all items, it will return all the positions. Okay, so the nodes. Okay, the positions in the tree. So it's not the item itself, but the position. Okay, so we have two iterators, items and positions. Next is root. So this will just return the root position. Okay, parent of the position will return the parent of the given position. So what is the parent position of this one? Okay, next, children of this position would be would return all the children of the given position. Okay, so pretty straightforward. Okay, so you can get the parent or the children of any given position or node. You can also ask if a certain position is the root node. Okay, so it will return true if that is the root node. You can also ask if that position or node is external or internal. Okay, so if it's external, it will return true if it doesn't have any children, if it's a leaf node. Is internal will return true if it has children. Okay, so and then the last two methods are swap items. So given two positions, you will exchange or swap the items inside position 1 and position 2. So you will not actually swap the positions, but you will only exchange the items. Okay, so the positions will stay in place, but it's only the items that are swapped out. Okay, and then finally you also have replace item. So given a position and the new item, so you will update the item in that position with the new item that is given, and you will also return the old item that was overwritten. Okay, so it's like an update for a certain position. Okay, so those are the methods for the tree interface. Okay, so that is the tree, and now we are ready to focus on the specific type of tree that we want to discuss or focus our discussion on, which is the binary trees. Okay, so a binary tree is, it's actually really simple. It's just a tree with the following properties. So each internal node has at most 2 children. Okay, so less than or equal to 2 children. So it could have no children, 1 child, or 2 children at most. Okay, so since we have 2 children at most, they are ordered. Okay, so you specify whether it's the left child or the right child. Okay, so you don't it's not unordered. You don't just mix that you have A and B, that A could come before B or B could come before A. It has to be specific. Is A the left child or is B the left child? Okay, okay, yeah, so the children are ordered basically. Okay, so that's it for binary trees. The children are ordered, and you have at most 2 children for the internal nodes. Okay, so it kind of looks like this. So this is an example of a binary tree. So you'll notice that all nodes either have 0, 1, or 2 children. So for example, here A only has 2 children, B also has 2, C has 2, E has 2, and then the rest are leaf nodes. Okay, so this is a binary tree. Some applications of binary tree include arithmetic expressions, for decision trees, and then binary search trees, which we will discuss in a later video. Okay, so how can we use this for arithmetic expressions? So for example, if you want to figure out how to resolve this arithmetic expression here, you can use a tree to visualize it, right? So 2 times 1 minus A plus 3 times B. So the internal nodes are operators, and then the external nodes are operands. So this just means that you need to process, since we have a parenthesis here for A minus 1, so you have to process this first, A minus 1, and then whatever is the result of that would be multiplied with 2. right? So you have the 2 times a minus 1. So that would be right here. And then whatever is the result of that would wait, because we have to figure this one out first. 3 times b, so that would be here. And then the result of this 2 would be added here, right? So that would be the whole 3 now. Okay? So yeah, that's how you can use trees or binary trees for arithmetic expressions. Okay? Next, you can also use this for decision trees. So if you've seen a decision tree before, it's just a series of questions with like a yes or no answers, or even other decision trees have like options A, B, C, and so on, right? But the idea is still the same. You have options. So for the internal nodes, you have the questions, and then for the external nodes or the leaf nodes, you have the decisions itself. So for example, here, are you a mammal? If it's yes, are you bigger than a cat? If it's yes, you're a kangaroo. If it's no, you're a mouse. And then if you said no to the mammal question, do you live underwater? If it's yes, you're a trout, you're a fish basically. If it's no, and then you ask, can you fly? If it's yes, robin. If it's no, it's a snake, something like that. So you've probably seen applications like this that guesses your hidden object or item after asking a few questions, right? So that is implemented by a decision tree. Okay, so those are some applications of binary trees. Okay, so next, let's take a look at the interface of the binary tree itself. So the binary tree extends the tree ADT. So that means that it will inherit all of the methods of the tree ADT. So the ones that we mentioned earlier, like the size is empty, root, children, is root, is external, is internal, and so on. All of those methods would also be inherited by the binary tree. Okay, but it also has additional methods like left child of p, so it will return the left child position of this particular position, and then you also have the right child, which will return the right child position of this given position p. And finally, you also have the sibling method. So given a position p, what is the sibling, if there is any, right? So if this p here is the left child, then it will give you the right child, and vice versa. So something like this. If you have like A, B, C, D, E, so if I call left child of B, that would return D, right? Because that is the left child of B. If you go right child of, let's say, A, then that would be C, because that is the right child of the node A. And then the sibling of E would be D, right? So E is the right child, so you go to the parent and then get the left child, the opposite, so that's D. And then for the sibling of B, that would be C, because B is the left child of A, so you go back to the top and then get the opposite, which is the right child, and then you get C. Okay, so that is the sibling. Okay, so yeah, that's the interface. We only listed a few here because it already inherits all of the methods of the tree ADT, so we don't need to list it again. Okay, now some additional terminology for binary trees. So first is a balanced tree. So a balanced tree is when the leaves, all of the leaves have depth h or h minus 1, meaning the height of the tree, or height minus 1. Okay, so for example here, the one on the left is a balanced tree because the leaves which are found here, so you have the leaves are those without any children, right? So that would be E, G, H, I, and then J, K, and L. So those are the leaf nodes. You can find them at the last level, right? So this is depth 0, this is depth 1, 2, and 3, and then the height is 3, right? So it's either at depth 3 or at depth 2, which is fine because it's either h or h minus 1. Okay? However, the one on the right is not a balanced tree because the leaf nodes are here. So you have E, G, you even have D here, I, K, and then L. Right? So what are the levels here? So this is level 0, 1, 2, 3, and 4. But where are the leaf nodes? You have ones in level 4, level 3, level 2, and even in level 1. So this is not a balanced tree because it should only have been on the last 2 levels, okay, for it to be balanced. Okay, so I hope that is clear for balanced trees. Let's go to the next one. So that is for trees in general. For binary trees, a balanced binary tree is when it's kind of similar, but it's more specific because it's binary tree, right? So the nodes at depth 0, 1 up to h minus 2 should have 2 children. Okay, so all of them must be filled up with 2 children. The ones at h minus 1, the one at the penultimate level or the second to the last level, could have 0, 1, or 2 children. Okay, so it could be a leaf, it could have 1 child, or it could have 2 children still. Okay, but the ones at the last level should have no children at all. So they must all be leaf nodes. Okay, so that is a balanced binary tree. Okay, so let's see an example. So here, so at for let's focus first on the left tree here. So the height of this tree is 3, right? Because the maximum depth is also 3. So at level 0 and 1, all of the nodes have 2 children. So A has 2 children, B has 2 children, C has 2 children. On the h minus 1 level, which is 2, right, the second to the last or the penultimate level, some nodes have 0 children like E and G, so they are leaf nodes. Some nodes have 1 child, which is D right here, it only has 1 child. Some nodes could also have 2 children, which is F, like I and J. Okay, but at the last level, which is at level 3, all of them should be leaf nodes. They must have no children. Okay, so this one is a balanced binary tree. Okay, the one on the right is not a balanced binary tree because you have this one right here, okay, which is a leaf node. When supposed to be, it should be from 0 to h minus 2 should have 2 children. At h minus 1, it should be 0, 1, or 2, but at level h, it should be 0. Okay, so this would be our 0, 1, 2. This is level h, this is level h minus 1, right? So at this level, are they all leaf nodes? Do they have 0 children? Well, it's still okay because I and J are leaf nodes, right? Now, how about at level h minus 1? Do they have 0, 1, or 2 children? Yeah, it's still okay because at this level, you have G, which has no children, H, which has 2 children, so it's still fine. However, when we go to the previous level, which is D is equal to 2, it should have 2 children for all nodes, right? But you have D here, which has no children, and E here, which also has no children. So this one is failed. Okay, so this is not balanced. Okay, so yeah, that is balanced binary trees. Okay, next, another term is something called the proper binary tree. So a proper binary tree is when each node either has 0 or 2 children. So you can't have one child only. If you have a child, it must be a pair of left and right child. Okay, so you either have no child or 2 children. Okay, so that is what you call a proper binary tree. There's also something called the complete binary tree. So a complete binary tree is when all levels are completely filled except maybe the last level. So you have an exception of the last level, which could have some nodes that are extra, okay? Like it's not all the way filled up at that level, and you fill this up from left to right. Okay, if there is a last level that has extra nodes, it should be filled up from left to right. There should be no skipping. Okay, so that is a complete binary tree. And finally, a full binary tree is also completely filled at all levels, and there should be no missing nodes. So for earlier in complete binary trees, you have like a sort of a leeway wherein you kind of give exception at the last level, so you could still have some nodes that are extra as long as you fill them from left to right. But here, it should be completely filled at all levels, and there should be no missing nodes. Okay, so all leaf nodes are at the last level, at the level h or the height, and all the other nodes should have 2 children. Okay, so let's see an example of a complete binary tree and a full binary tree. So this one is a full binary tree, the one at the right, because you'll notice that everything is filled up at all levels, right? So at level 0, you have A, and then it has 2 children. So at level 1, it has a left child and a right child. And then for at level 2, B has a left child and a right child. C also has a left child and a right child. So all the 4 nodes are filled up. And then at the last level, which is 3, all nodes are also left and right children. So you have H and I, J and K, L and M, N and O. Okay, so this is a full binary tree because you don't have any holes in the tree. Okay, the one on the left is just a complete binary tree because it's still complete at level 0, at level 1, and at level 2. But when you reach the last level, there are some extra nodes, which is fine for a complete binary tree. Okay, so you have that exception at the last node, and it's filled from left to right. So you start at the D, okay, H and I, and then from E you have the J. But if you have something like K here, then this is not a complete binary tree anymore because you skipped over some spaces here. Okay, so yeah, that's a complete binary tree and then a full binary tree. Okay, so those are some terminologies for binary trees. So now we are ready to look at some implementations of binary trees. So how do we implement them so that we could use them in our codes? So we'll look at 2 implementations. First is using an array, and the second is using a linked structure, okay, using nodes. Okay, so let's start with the array binary tree implementation. So for the array binary tree, we will use an indexing scheme. Okay, so since we're using an array, this indexing scheme will tell you at which index should you insert that position into. Okay, so this is the indexing scheme. If it's the root, you insert it at index 1. So the index of the root is always at 1. Okay, the left child of, let's say, node A would be placed at 2 times the index of node A. Okay, and then the right child of node A would be at 2 times index of A and then plus 1. Okay, so the left child and the right child would be next to each other because you have 2 times index of A and then 2 times index of A plus 1, right? So the right child is right after the left child, basically. Okay, so let's see an example of that. So if this is your binary tree here, so you have A and then children B and C, and then for B, children D and E, C, children F and G. This is how it will be stored in the array. Okay, so you'll notice there is no element at index 0, so we'll just leave that blank. Okay, because root is always at index 1. Okay, now B is the left child of A, right? So it should be at so A is at 1, right? And then B, since it's the left child, that should be 2 times 1 left of A, since A is 1. So that's why it's at index 2. And then C, which is the right child of 1, that would be 2 times 1 plus 1, which is at index 3. Okay, that is why it's at index 3. And then for D, left of B, left child of B. And then B is index 2, right? So this would be 2 times 2, which is at index 4. And then E, which is the right child of B, that would be, this is also index 2, so that's 2 times 2 plus 1, so that's at index 5. So you have index 5 here. And then you can also do the same for F and G. So for F, that would be 2 times the index of C, which is 3, so that you have 6. And then for G, that would be 2 times the index of C, which is 3, and then plus 1, so you have 7. Okay, so this is how it will look like in the array. Okay, so yeah, that is the indexing scheme for array binary tree. So what are the advantages if you use this array implementation? So the implementation is actually really simple because of once you have the computation of the left and the right child, of where to put the left child and the right child, and then the root is just simply at 1, then everything is done basically, right? You can also easily access the nodes using the index and just compute the appropriate index, and then you can just easily access the nodes, right? And it also has fast running time, which is O of 1 constant for all methods except for the iterators, because of course for iterators you have to iterate through everything, right? So everything is constant. Okay, so let's see why. So for iterators, those are the exceptions, right? So for items and positions, since you have to go through all of the items and all of the positions, then obviously that would be O of n, or where n is the number of items in the tree. So since you have to return all items and all positions, then naturally you have to traverse through all of them. So that's O of n. Now, how about the others, the rest of the methods for binary trees? Why are they constant? So for root, it's constant because to get the root node, just go to index 1, right? And then for the parent of this node, you just divide the index by 2, okay? And then you go to the parent. And then for the children, you just go to index times 2, and then index times 2 plus 1, then that would be your children already, okay? And then same for left child and right child. So for left child, you go to index times 2. For right child, you go to index times 2 plus 1, right? And then you already get the left child and right child. And then for sibling, it's quite tricky, but basically if you have, you can just go either -1 or +1, depending on whether you're the left child or the right child. Okay, so for example, here, if you have A, B, C, so let's just keep it simple and just have this small one. So this would be at index 1 because it's the root. This will be at index 2. This will be at index 3, right? So we have 0, 1, 2, 3. So this is A, this is B, this is C. Okay? So, for example, if you ask what is the sibling of the node at B. So, sibling of B, wherein the index is 2. So, since this is even, you know that this is the left child. So, you need to get the right child. So, you just add +1. So, you get 3. And then the index of 3 holds C. So, this will return C. Okay. Now, for the sibling of C, on the other hand, sibling of C, C's index is 3, so it's odd, so we know that it's the right child, right? Because if it's 2 times index, it's even, this is the left child. If it's 2 times I plus 1, this is odd, and that's obviously the right child. So based on the index whether it's even or odd, you can determine if it's the left child or the right child. So if it's the right child, you just subtract 1 from the index, so you get 2, and then you get the sibling, which is B at this point. Okay, so that is also constant time because that's just 2 steps, right? So you get the index and then access the index. Okay, so that's still constant. And then next is root of P. So just check if the index of this position is 1, because if it's 1, then that's the root node. Is external. Okay, so how do you check if the node is external or not? Is it a leaf node or not? Okay, so you have to check whether it has children or not. So you go to 2 times the index and 2 times index plus 1, and if both of those are empty, then that is an external node or a leaf node because there are no children, right? But if there are nodes there, then that is an internal node, so you return false. So for is internal, that would be a similar process, but it's just the opposite. So you return true if there are children in either one of the index times 2 and index times 2 plus 1. Okay, so that is still constant time. Okay, and then finally for swap items, you're already given P1 and P2, right? So you just have, that will just take like 3 lines or 3 steps. So you store the item of P1 in a temporary variable, and then you make P2 is equal to P1's item, and then P1 is equal to P2's item, and then P2 would get the item from the temporary variable, and then they're already swapped, right? So it's fairly straightforward since you can get the indices already. Okay, and then for replaced item, since you can also directly access the position based on the index, so you just update the index entry, and then you're done. You can already replace the item. Okay, so all of it is in constant time. Okay, so it has very good running time performance. However, for the memory, this is where it's kind of tricky, because for the memory, to analyze the memory performance, let's first define some variables. So let's let n be the number of nodes in the tree. Okay, so how many items are there in the tree, basically, because there is a 1-to-1 correspondence for number of nodes and number of items, right? And then let's let I max, the maximum I or maximum index, be the maximum value of the index of the node. So what is the largest possible index of any node or any position? And then let's let variable C be the array capacity. So how large or how big should the array capacity be? So it should be I max plus 1, right? Because whatever is the biggest maximum index, right? You will add plus 1, and that is the capacity. Why will you need to add plus 1? Because remember that index 0 is empty, right? So let's say if your maximum index is 15, so you know that you will use all the way up to index 15, so you need to at least have a 16 capacity array, right? So 15 plus 1, so that it could hold up to index 15. Okay, so given these 3 variables, in the best case for the array binary tree, this is when you have a full balanced tree, right? Wherein all of the array slots are occupied except for 0, of course. Like for example, the one that we saw earlier, wherein you have A, B, C, D, E, F, G, something like this. So this will be at 1, 2, 3, 4, 5, 6, 7. So if you have 7 nodes, what would be the size of the array? That would be 8, right? So you have 0, 1, 2, 3, 4, 5, 6, 7. So this is a size 8 array or capacity 8 array. Okay. So something like this, right? So A is at index 1, B is at index 2, C, D, E, F, and G. That's the best case because there is no wastage except for the empty slot here at 0, but that's negligible because it's only one space, right? But what is the opposite of this? What is the worst case? Or before we go to the worst case, um, for this best case, um, the memory consumption would be O of n, right? Because let's say you have the I max is n, and then you have plus 1, so you have, that's still O of n because it's just n plus 1, right? So the maximum array index here was 7, and then you used an array of size 8, so that would be 7 plus 1. So n plus 1 is still O of n, right? So that is at the best case. However, what is the opposite, the worst case? For the worst case is when you have a highly unbalanced tree, okay? And this will lead to many empty slots. And why is that? Okay, so let's draw some here. So let's say that this is A, B, C, D, E, F, and G. So how many items do we have? So we have 7 items, right? But your I max is at 15. Okay? Because A should be at root, the root index, which is 1. Then B is times 2, so at 2. C is times 2 plus 1, so at 3. And then D is the child of C, which is at index 3, so that should be 3 times 2, so that's 6. And then the sibling is at plus 1, so that's 7. And then F is the child of E, which is at index 7. So if you multiply by 2, that would be at 14, and then plus 1, 15 for the sibling G, right? So you only have 7 nodes, but what would be your capacity? That would be I max plus 1, which is 15 plus 1, which is 16 already. So you'll notice the wastage from 7. You only need 7 nodes, but you are allocating an array of capacity 16. Okay, and if we actually work out the math behind this, so we have defined this earlier, right? So the n is 7, I max was 15, and you'll notice also that the height was 3 earlier, right? Because you have here, this is level 0, this is level 1, this is level 2, this is level 3. So this is the maximum depth, so this is the height of the tree. So height of the tree is also 3. Okay, so going back here, so these were our variables, right? You have 7 nodes, the height of the tree is 3, and the maximum index was 15. Okay, so how did we get the height? We got the height by actually dividing n minus 1 by 2. Why did we do that? Because okay, so where is the okay, so since we have n what do you call this, n nodes, but except for the root, okay, except for the root, which is alone in its own level, so we'll remove the root, so we'll take minus 1. And then how many levels are left? So we have 3, right? But how do we get 3? We get 3 because at each level there are 2 nodes, right? So we'll divide this by 2. Okay, so n, which was 7, so 7 minus 1, this is 6, over 2 is 3. So this is our height. Height is equal to 3. Okay, so yeah, so that is how we computed for the height. Okay, going back here, okay, so n minus 1 over 2 siya. For the maximum height, how did we compute for the maximum height? That would be 2 raised to h plus 1 and then minus 1. Okay, why is that? Because where is the okay, it's here. So our height was 3, right? So if you have 2 raised to 3 plus 1, where 3 is the height, this would be 2 raised to 4, which is 16, right? But 16 is the size of our array, okay? But if we're only using the index, the maximum index would be minus 1. So that would be 15. Okay, so that's why you have the 15 as the I max. Okay, so we have these equations here. Wherein h is equal to n minus 1 over 2, and you also have I max is equal to 2h plus 1 minus 1. Now, if we combine these two, wherein we substitute the value of h here with n minus 1 over 2. So if h is equal to n minus 1 over 2, h plus 1 becomes, so this would be n minus 1 over 2, and then plus 1, so we could have 2 over 2, right? So that we could combine the numerator and the numerator terms. So n minus 1 plus 2 all over 2. So n minus 1 plus 2 would be n plus 1, right? Because 2 minus 1 is 1. This would be n plus 1 over 2. So this whole thing here could become 2 n plus 1 all over 2, then minus 1. Okay, so that's why you have this one here, n plus 1 over 2 minus 1. And then if you remove that, so if I max is that value, if I max is 2n plus 1 over 2 minus 1, so remember that our capacity was computed as I max plus 1, right? Because it's the maximum index, and then you add 1 for the index 0. That would be your array capacity. So if you plug in this value for I max, you will have this. So that would be 2n plus 1 over 2 minus 1, and then plus 1, so this 2 will cancel out. And basically you have capacity is equal to 2n plus 1 all over 2. But this is in O of 2 raised to n, right? Because that is a 2 here, and then this is basically an n. You just have an extra plus 1 and then divide by 2. But this is still a factor of n, right? So that would be 2 raised to n, which is, as we know, this is exponential, which is bad. Okay? So at the worst case, if you have a highly unbalanced tree, binary tree, then you will get exponential memory. Like for example, you only need 7 nodes, but then you need a 16 capacity array. What more if you only need 100 and then it's super unbalanced, right? So it would be like this. It would be, so you go deeper and deeper, and then you would need a lot more space, which wherein a lot of the cells are actually empty. There's a lot of wastage, right? So that is the disadvantage for your array binary tree. It's when you have a highly unbalanced binary tree. Okay, so for the memory performance, it's poor in general because you don't know what the structure of the binary tree is in advance. Okay, so if you are lucky and you get a full balanced tree, then that is the best case. You get O of n memory because you basically have like a full array also. But at the worst case, you could have an exponential amount of memory, okay, if you have a highly unbalanced binary tree. So this is bad. Okay, so that is the disadvantage for array binary tree. Okay, so next, let's look at the second implementation for binary trees, which uses a linked structure. So we call this the linked binary tree. So for the linked binary tree, it will use a new type of node. Okay, so similar to the SLL node and the DLL node, we call this the binary tree node, or BT node for short. Okay, so for the BT node, it also implements the position ADT. Okay, so it will abstract out the concept of nodes so that we don't expose the underlying implementation. So it will have three things. Okay, so it will hold the item, it will have a link to the parent, and it will have links to the left child and the right child. Okay, so it kind of looks like this. So you have four things. Okay, so the element or the item itself, link to the parent node, link to the left child, link to the right child, and then if there are no children, then they will just be null. Okay, so that this is how a BT node looks like. So obviously the methods are just pretty straightforward. They're just getters and setters, right? So you have the element, so you get the element, set element x, and then get the parent, set parent, get left, set left, get right, set right. So it's basically just getters and setters for the four private properties, which are the element, parent, left, and right nodes. Okay, so yeah, I don't need to expand on this further. If it's the root node, then obviously the parent pointer will be null because root nodes don't have any parents. And if it's a leaf node, then the left and right child would be null also because we know that leaf nodes don't have any children, right? So yeah, that's BT node. So a binary tree that looks like this, A, B, C, and then B has children, D, E, would look like this in the linked binary tree. So you have 5 nodes representing the 5 nodes here in the tree. So you have 5 BT nodes. Okay, so you have the A here, which is the root, then it's pointing to B, and then A is referring to B as its left child, and then B is pointing back at A as its parent. Okay, so you have the two-way pointers connections. Yeah, and then at the leaf nodes you also have null pointers since they don't have any children. Then same with the parent of A, which is the root. Okay, so those are pointing to null. Now how about the performance of the linked binary tree? It has good memory. It uses O of n, one BT node per tree node, which is good because there are no empty slots unlike in ArrayBinaryTree. So there is no wastage, right? Because there's a one-to-one correspondence. You kind of have extra because of the links, but that's just a constant factor which is negligible. Unlike in ArrayBT, wherein at the worst case you could have like the exponential amount of memory, which is really bad, right? So at least this one is there's a one-to-one correspondence between the BT node and the tree node. Okay, and although the BT node has like 4 extra links, it's fine. Okay, that's just a constant number. 4 times n is just O of n still, right? Okay, next, for the running time, it also has good running time, which is O of 1 for all of the methods. Of course, except the iterators, because as we said, iterators will have to go through all positions and all items, so that should be O of n naturally, right? So items and positions are O of n because we have to traverse all items and all positions since they are iterators. And then for root, this would be O of 1 because the linked binary tree should keep track of the root node. Okay, and then for the parent of P, then you just ask the BT node what is the parent of this node, right? Then for the children, you just get the left child and the right child. And then for left child, right child, obviously there is a direct method, the direct correspondence in the BT node, so this is pretty straightforward. And then for the sibling, you go to the parent and then you go to the opposite. So if you're a left child, you get the right child. If you're the right child, you get the left child. Okay, so it's still constant because that's just like 3 steps, right? Go up, then down, or 2 steps even. Okay, and then is root, we'll just check whether the saved root node is the same as the one that you passed in. Is external and is internal is similar process. They just return opposite things, right? So just check whether there is at least one node in either the left child or the right child, and that would be an internal node if that's true. Otherwise, if both children are null, then that would be an external node or a leaf node, right? So you can do that directly because you have these properties from the BT node itself. Okay, and then for swap items, you just simply get the items of the 2 BT nodes and then just swap them. And then for replace, you can also simply update the item because BT node also has the set element. Okay, so yeah, everything is in constant time for linked binary tree. Okay, so yeah, that's it for the implementations. And then now we are ready to go to the final part of our lecture, which is about tree traversals. Okay, so what are tree traversals? They are a systematic way of accessing or visiting all nodes of a tree. Okay, so if you want to um, go on a tour of the tree, so if you want to access everything, so you use a tree traversal algorithm. In tree traversals, each node is visited exactly once, so you don't repeat or you don't visit them twice. Okay, so a tree traversal will produce a linear ordering of the tree nodes. So depending on your traversal algorithm, you have you could produce a different ordering. Okay, so whether it's pre-order, post-order, in order, or level order, so it depends. Okay, so why do we need tree traversals? So for example, if you want an iterator for the tree wherein you could go through the different nodes or different items, so this is this is applicable. If you want to print out each node's label, that's also another purpose. And then if you want to search for a node, you can do so in a systematic manner so that you don't have to repeatedly search a particular branch, right? So if you've been through that branch, don't repeat going through it so that it becomes efficient for your search process, right? So these are just some applications for tree traversals. So traversal and searching comes hand in hand because if you're traversing, you are doing a journey or doing a tour of the tree, then you can piggyback on that if you're doing a search, right? Since you are walking through the tree, then part of that could be looking for a certain node. Okay, so yeah, traversal and search are hand in hand. So we will discuss 4 different tree traversal algorithms. You have the level order, pre-order, post-order, and in-order. And then we divided this into 2. So level order comes from the BFS or the breadth first search. And then the other 3 comes from the DFS or the depth first search. Okay, so before we actually look at the tree traversal algorithms, let's first review the difference between the BFS and the DFS. Okay, I'm sure you've already encountered these terms before, probably in a previous ComSci subject, but let's just review them to refresh your memory. So breadth first search or BFS is a tree search and traversal algorithm wherein you explore the nodes in layers. Okay, so you process the nodes layer per layer, and then at each layer you process the nodes from left to right. Okay, so you start at the top layer and then you go to the next layer and then you go to the next layer and so on until you reach the bottommost layer, and then at each layer you go from left to right. So in its implementation, it uses a queue since you have like a first in first out process, right? So for example, here in this tree, BFS will process it like this. So per layer, right? So it will process layer 1, so you have A, and then it will process this layer here, so you go from B, D, and then C, so from left to right. And then the next layer will have E and then F, and then at the last layer you have G and H. Okay, so pretty straightforward, right? BFS per layer, okay, from top to bottom. So you start at the root and then you go down, and then at each layer you process from left to right. Okay, so that's it. So that is BFS or breadth first search. So it's called breadth first search because breadth refers to the width, right? you're going horizontally. Okay. Now the other one is called depth first search, or DFS. So it's also a tree search and traversal algorithm, but this time you explore as deep as possible. Okay, and then once you reach a dead end, you backtrack. Okay, so backtrack only if necessary, but as long as you can still go down, you can go further to the bottommost layer, then you proceed. Okay, so it's very aggressive in exploring, like in a maze. So in a maze, you probably just go forward until you reach a dead end, and at that point, you just go back and try another pathway, right? So unlike in BFS, wherein it uses queue, here it uses a stack, or it could also use recursion, because recursion has an implicit stack, okay, and its implementation. So yeah, so that's DFS. So let's see an example of DFS. So you start at the root, which is A. Okay, so this is the first one. And then you go down here. So this is the second one. You visit B. And then you can still go down here and then visit E, right? But at E, you're stuck. This is a dead end. So you go back to B. And then at B, you can still go to F, right? So you go down here. This is the fourth one that you visit. And then at F, you can go to G. You can go down. So this is the fifth one you visit. And then at G, you're stuck. So you go back to F. And at F, you can still go to G. Not G. H. You can go back to H. So this is the sixth one that you visited. And at H, you are stuck. So you go back up to F. And at F, there is no more children to visit. So you go back up again. And at B, you found that you've also visited all children. So you go back up to A. And then you process A's next children. So you go down to D. So this is already the seventh one that you encountered. And then go back up because it's a dead end. And then go to the next child of A, which is C. And then that's the eighth one. And then C is also a dead end. So you go back up. And then at this point, you've already examined all of the children of A. So then you stop. Okay? So that is depth first search, or DFS. So you go as deep as possible, like here, going to here. Then once you're stuck, go back up, and then go as deep again as possible. Then go back up, and then go as deep as possible again. Okay? So that is DFS. Okay, so when is it appropriate to use either one, BFS or DFS? So for breadth first search, or BFS, you use this when the depth of the tree can vary. Okay, so what do you mean by this? So for example, if it's unbalanced tree, like for example the tree kind of looks like this, like that, then like that, then like that, then for this one maybe something like that. Okay, so this one is highly unbalanced compared to something that maybe looks like this, wherein it's kind of balanced at least, no? Something like this. This one is kind of balanced, whereas this one is imbalanced, the one on the left, because it's so deep here, whereas the other levels are kind of shallow, the ones here. So if you get this kind of node tree here, and then you use DFS, then you're very unlucky because you go as deep as possible here, and then you go backtrack, but then maybe what if the thing that you're looking for is already at the at shallow level, right? So it would have been better to use BFS if you went layer per layer. Okay, so you also use BFS when you only need to search part of the tree. Okay, so if you don't need to search everything, then you just go layer per layer. And also when you know that the solution is not far from the root node, then it's much better to go BFS, because maybe if you get lucky, after some layers you can find the solution already. But then if you use DFS on the other hand, what if the solution is at the, let's say, at a shallow level, but it's at the right part, let's say here, the solution is here. Okay, if you go DFS, so this level, and then at the third level you find it, right? Because you're going level per level. But if you go DFS and then the solution is here, then you'd have to go down deep here and then go back up and then go back down, up, go back down before reaching the solution, right? So it's kind of it will take a longer time. Okay, so when you know that the solution is not far from the root, then it's much better to use BFS. So use a per layer approach. Okay, so next, how about the performance of BFS? If we let B be the branching factor, okay, or the number of nodes or children, okay, so if it's a binary tree, the branching factor would be 2, right? And then S is the depth of the shallowest solution. So it actually the performance of BFS depends on where the solution is. Okay, so whether the solution is at the bottommost or somewhere near the root, so it will affect the performance. Okay, so both the running time and memory is B raised to S. Okay, so like let's say if say the branching factor is 2 because it's a binary tree, and then let's say the solution can be found at the shallow depth, like let's say 3, that would be 2 raised to 3. But if the solution is at a deep part of the tree, like let's say at level 15 pa, then that would be 2 raised to 15, which is a lot bigger. Okay, so it all depends on the branching factor, okay, and the depth of the shallowest solution. So the bigger this goes, the worse the running time is, and the memory also. Okay, so why is the memory also big? Because for example, as you go per level, as you go deeper, for example, if you're already at this level, you're keeping all of the previous nodes in memory, right? Because you are checking, like for example, how do you get at this level? You get the children of this node right here, and then after that you get the children of this node here, then this node here, and then this node here, right? And then after that, once you get these nodes, you also save the nodes at this level because you will use that to process the next level. Okay, that's why you have also exponential memory. Okay, now how about for depth first search, or DFS? So you use this when you actually need to search the entire tree. Okay, so if you need to go through the whole thing, then just use depth first search, because maybe you'll get lucky and you find it at the left part, okay, of the tree, so you can stop early. Another advantage of DFS is it's easier to implement compared to BFS, okay, because you just go straight forward, and then once you hit a dead end, you go back. Okay, also requires less memory than BFS, because unlike BFS, which stores the whole previous level, it only stores the for DFS, it only stores the parents. Okay, so we mentioned this earlier, right? All nodes at the previous level are stored for BFS. That's why it has a exponential memory. But at DFS, you only store the list of the parents, so that you know where to backtrack. So for example, if you're going down, you just keep the list of these nodes here that you've encountered. Then once you go back up, then those are removed also. Once you go back up, they are deleted. Okay, so if you go back to the shallow part, then the memory that you use will be lesser, right? So you don't need to store other nodes at that level. You only need to store whatever nodes you passed by, so that you know where to backtrack. Okay, so yeah, so in terms of memory, DFS is more is better because it uses less memory. Okay, so for DFS, if B is the branching factor and then M is the maximum depth of the tree. So unlike BFS, which relied on the depth of the shallowest solution, here we actually rely on the maximum depth of the tree regardless of where the solution is, because we are going as deep as possible, right? So if these are the two variables, then the running time would be B raised to M. Okay, so it's also exponential in terms of the branching factor and the max depth. And then so the bigger the depth, the max depth is, the more time you need to spend, because you will go as deep as possible, right, for DFS. Okay, and then for memory, this the good news for DFS. It's only polynomial, right? B times M lang siya. Okay, branching factor times the max depth, because this is only like the what do you call this, the list of parent nodes that you've passed by. So it's at least better than BFS. Okay, so that's the difference between BFS and DFS. So again, for BFS you go per layer and then go from left to right, and then for DFS you just go as deep as possible, and then once you hit the dead end you go back. Okay, backtrack. Okay, so let's now go back to the tree traversal algorithms. So first tree traversal algorithm is the level order traversal. So this one uses BFS, and it works exactly just like how BFS works. Okay, so you visit every node on a level by level basis, in a per layer basis, and then visit all nodes on that level before going down to a lower level. Okay, and then you also process nodes from left to right. Okay, so it works similar to BFS basically. Okay, so in here for our level order traversal, for this tree here, binary tree, so we'll go first at level 0, so that would be at A, and then the second level, or the level 1 basically, you go from left to right, so that would be B and then C, and then the third one would be at E and then F, and then the last level is here, so that would be G and then H. Okay, so that is the level order traversal. Okay, A, B, C, E, F, G, H. So A, B, C, E, F, G, and then H. Pretty straightforward, right? Okay, so that's level order traversal, basically BFS. Now next are the three DFS traversals, but they kind of differ in a subtle way. So first one is pre-order traversal. So for pre-order traversal, this follows DFS, okay, depth first search. But then for you to traverse in using pre-order, first you visit the root, and then you traverse the left subtree, and then you traverse the right subtree. Okay, so if it's pre-order, it's root, left, and then right. Okay, so we use this for copying trees. So if you want to copy a tree, you do a pre-order traversal so that you can copy the parent before the children. So that's why you take care of the root first, or the parent node, before doing the left subtree and then the right subtree. Okay, so pre-order is root, left, and then right. So let's see an example. So here, so again, this should be root, left, and then right. So here, the root is A, right? So we'll take care of this first. That's A. And then we'll go to its left subtree, which is here. And then in this left subtree, the root is B, right? So B is processed or visited. And then at B, we will process its left subtree, which is at here. Okay, so at this one, it's only E, so you have E here, and then it's done, right? So after processing the left subtree of B, we'll process the right subtree of B, which is right here. Okay, so this is the right subtree of B. At the right subtree, you have F as the root, so you process that one first. Okay, so you have F, and then you process the left, which is G, and then you process the right, which is H. Okay, and then you're done because the F sub 3 is processed. So the B sub 3 is also processed, right? So you're done with the left sub 3 of A. After that, you need to process the right sub 3, which is at C. Okay, but there's only C here, so just process C. So that is the pre-ordered traversal. A, B, E, F, G, H, C. Okay? So if I try to erase the markings here first. So again, that is start here, A, and then go to the left, and then process the root first, so that would be here, which is B, and then go to the left, so that's E, and then it doesn't have any children, so you don't need to process any left child or right child. And then after that, go back to B, process its right child, which is F, and then this is the root, so this is processed first, and then left child is F, right child is H, F's left child is G, H is the right child, right? So this is processed. Then after that, the whole B sub 3 is processed. So you're done with A's left, so you go to A's right, which is C. So this one is the last one. Okay, so yeah. So that's the pre-ordered traversal, A, B, E, F, G, H, C. Okay, so root first, and then left, and then right. Okay, so next one is post-order traversal. For post-order, you traverse the left sub 3 first, you traverse the right sub 3 after that, and then you visit the root as the last. Okay, so even if you're already at the root node, you will not process it first. You will go to the left sub 3 first, and then after that the right sub 3 before processing the root. Okay, so you actually use this for deleting trees, so that you delete the children before the parent, so that you don't have any like floating nodes. So delete all children first before deleting the parent. Okay, so that's post-order traversal. Left first, right, and then root. Okay, so let's see that in an example. So post-order is left, right, and then root. Okay, so starting at the root, which is at A, well, we will not process A yet. We will go to its left sub 3, which is right here. Okay, so we'll process this one first. But at this sub 3, B is the root, but we will not process that one yet, because we'll have to go to its left sub 3, which is E. Right here. But at E, it's the only node there, so there's no left child, there's no right child, so E is the root, so this is the first one it will process. Then after that, we'll go back to B, but B still has a right child, right? So we'll process that one first after processing its left sub 3. So we'll process the F sub 3 right here. But at F is the root, so we won't touch that one yet. We'll go to the left, which is G. So this is the second one. And then we'll go to H, which is the right sub 3, right child. That's the third one. And then we already processed it since it doesn't have any children. And then after processing the left and right, which is G and H, we can now go to F, which is the root of this sub 3. So this is the fourth one. Okay, and then after processing the sub 3 of E and sub 3 of F, we can now process B, which is the root of this sub 3. So this is the fifth one. So far we have E, G, H, F, and then B. So we're now done with the left sub 3 of A. So we'll now go to the right subtree of A, which is C. But since C is all alone, so we can just process that directly. That would be the sixth one, that would be C. And then the last one would be the root, which was A. So you have this as the seventh one right here. Okay? So again, that is E, G, H, F, B, C, A. Right? So that is the post-order traversal. So one more time, you go to the so you go to the left, right, right before root. So you go to the left, you go to the left, and then this is already the root, so this is the first one. And then you go back to the root, and then go to the right, but there's still children, so you go to the left, so this is 2, and then go to the right, which is 3, and then since all of the children are processed, you can process the root here, which is F, and then it's 4. And then after processing the left and right child of B, B can be processed now, so this is the fifth one. And then after processing A's left, you go to A's right, which is C, and since it's all alone, you can already visit that. And then after processing the left and right of A, which is B and C, you can process it already as the last one. Okay, so that is post-order traversal. Left subtree first, and then the right subtree, and then the root. Okay, so yeah, that's post-order traversal. And then finally, the last one is called in-order traversal. So the sequence of processing would be, first we'll traverse the left subtree, and then after that you visit the root, and then you visit the right subtree. Okay, so it's kind of similar to post order, but the root, instead of being the last, would be the one in between. So after left, you visit root, and then you visit right. Okay, so we'll use this in binary search trees, which we'll discuss in a later video. Okay, so that's in order traversal: left, root, right. Okay, so let's see an example. Left, root, and then right. So in here, we'll start at A, but A is not should not be visited yet, because root should come after processing the left subtree. So we'll take a look at the left subtree first, which is this one. At the left subtree, at B, B is the root, so we'll have to wait after processing the left subtree of B, which is E. So at E, this is all alone, so we can process it already. So it's E. And then after E, we can visit the root now, which is at this subtree, this is B. So this is number 2. And then after that, we'll process the right subtree, which is right here at F. And then at F, we'll go to the left first, which is G, so that's the third one. And then the root, which is F, that's the fourth one. And then the right, which is H, which is the fifth one. So that would be G, F, H. Okay, so after processing the right subtree, we're done with the whole B subtree, because we've gone from left to the root to the right. So we're done with the left subtree of A. Okay, so we're now ready to process the root, which is now A. So this should be number 6. It's A. And then after that, the right subtree, which is C, which is all alone, so that's number 7. Okay, so E, B, G, F, H, A, C. Okay, so that is the in-order traversal. So again, it should be left, and then root, and then right. So that's why we have the this order. So from A, you go to the left. From B, you go to the left, and then this one is the first one. And then you go to the root, which was B. And then from B, you go to the right, but F has children, so you go to the left first. Then you go to the root, which is F, and then you go to the right. Then after processing B, you can now process the middle or the root one, which is A, and then process the the right part, which is C, and that's the last one. So you have E, B, G, F, H, A, C. Okay, so that is in order traversal. Okay, so if you want to practice, you can pause the video here and try to figure out what the pre-order, post-order, in-order, and then the level order traversals are for this given binary tree here. Okay? Okay, so make sure that you pause the video because I'll be discussing the solution in 3, 2, 1. Okay, so let's see what the different traversals are for this binary tree. So let's start with the level order traversal, which is just the BFS basically, right? So for level order traversal, we go the first level, which is 60. Second level, you get 20 and 70. So you go from left to right. And then the next level, you get 10 and 40. And then at the last level, you have 30 and 50. So that is your level order traversal. So 60, 20, 70, 10, 40, 30, and 50. So check if you got that right. And then we'll proceed to the next one, which is pre-order traversal. So remember that this is root, and then left, and then right. Okay, so the root, or let's just call it the parent for to differentiate it from the right, so that I don't use R for both. So the parent, and then the left, and then the right. So for pre-order, that would be, so the parent here is 60, so that's the first one. And then the left children, you get for the 20 sub 3, you have 20 as the root, and then the left is 10. And then for the right sub 3, you have 40 as the root, the left is 30, the right is 50. And then after processing the left sub 3 of 60, you go to the right, so you get 70. Okay, so that's 60. So this is the order: 60, 20, 10, and then 40, 30, 50. And then once this whole sub 3 is done, you go to the right sub 3, so you get 70. Okay, so that's the pre-order traversal. Next, we'll take a look at the post-order traversal. So for post-order, you have the left, right before the parent, right? So for post-order traversal, we go to the left of from 60, you go to the left, you get 20, and then you go to the left, you get 10. So this is the first one. Okay, so you have 10, and then you go to the right, sub 3, but here this another sub 3, so you go to the left first, so you get 30, and then the right, you get 50, and then next is the parent, right? So this is 40. This is the fourth one. And then after that, the parent of both 10 and 40, which is 20. So this is the fifth one. So you have 50. Not 50, but 20. Okay. And then after that, you go to the right, so you get 70. And then that's when you go to the parent, which is 60. So this is the last, 60. Okay, so 10, and then 30, 50, parent, this is 40, so get the left and right, you get 20, then the right is 70, get the parent 60. Okay, so that's the post order traversal. And then the last one, it's in order traversal. So you have left and then the parent before the right one. Okay, so let's erase the markings here. Okay, so you go to the left first, which is here, and you get to go to the left again. So first one is still 10, but after that you can process the root of the subtree, which is 20, so that's the second one. And then you go to the right subtree, but then you go to the left first, so that's 30, this is the third one. And then the right, before going to the right, you can process the root, which is at the middle, so that's the fourth one, it's 40, and then the right subtree is 50, right? So this is 50. And then after that, after processing the left subtree, you can process the parent, which is 60, so this is the sixth one. And then the last one is the right subtree, which is 70, which is all alone. Okay, so it's 10, 20, 30, 40, 50, 60, 70. That is the in order traversal for this tree. Okay, so those are the different traversals for this practice binary trees. Hopefully you got all of them right, and if not, then you can review and try to do it again and until you get the right answer. Okay, so that's also written here, the answers, right? So yeah, that's it for tree traversals. So, and also that's it for this video. So let's try to review what we've talked about so far. So we looked at trees, which are nonlinear ADTs that model a hierarchical structure. So you have nodes that have parent-children relationship, right? So each node has one parent, then the nodes can have multiple children, and then there should be no cycles in the trees, and there should be a unique path from the node to the root, right? There should be no two parents, okay, for each node. And then we also looked at specific type of trees, which are the binary trees. And in binary trees, your nodes could have either 0, 1, or 2 children. Okay, so at most 2 children. That's why it's called binary, right? And then we also looked at the two different implementations of binary trees using arrays, using the indexing scheme, right? So root is at 1, and then left child is at 2 times the index, and then right child is 2 times the index plus 1. And then for linked binary trees, we have using the BT node, which has a link to the parent, link to the left child, link to the right child, and then the item itself. Okay, and then we also looked at tree traversal algorithms, which were separated into the BFS traversals and the DFS traversals. So we reviewed the breadth first search and the depth first search, wherein BFS is appropriate for when the solution is shallow, right? So you go layer per layer. And then for DFS is when you need to search the whole thing, so you just go as deep as possible, and then once you reach a dead end, you backtrack. Okay, and then finally we talked about the different tree traversal algorithms that you can use to process or go through the whole tree in a systematic manner. So you have the level order, which is BFS, pre-order traversal, post-order, and in-order, which are all DFS traversals. So they vary in how they visit the nodes, right? So for pre-order, that would be parent before the left, before the right. Okay, so parent, left, right. So for post-order, it's left child, right child before the parent, and then for in-order, it's left child, parent, and then the right child. Okay, so that's all for this video. Hopefully you learned something new about trees and binary trees and tree traversals. For our next topic, we would talk about we would be discussing priority queues and heaps. Okay, so that's it for this video. If you have any questions, please don't hesitate to ask me, and I will see you next time.